All right, welcome back, everyone. Today's Tuesday, online day. Okay, so hopefully you are watching my desktop. How you doing? This is the last week of the summer. Today's Tuesday, so including today, three more classes. Okay, so today we are going to continue talking about Unit 4A. Okay. Unit 4A, center of gravity, centroid, geometric properties. Okay, so before we begin, let's take a look at updates. Okay, so hopefully you're watching my desktop. Is that correct? Can you see this? Good. So this is the new update, which is posted yesterday, Monday. Okay, the last week of Summer A, here is the MATLAB Symbolic Math Toolbox self-learning tutorial taken from EGR 115. Did you take EGR 115, by the way? Please raise your hand or react either way if you took EGR 115. There are a few people actually haven't taken yet or are planning to take it. Okay, so do you have any idea what I'm talking about? Symbolic math of MATLAB. Was this part of EGR 115 class you took? Not really?
I never really took in mine.
Hmm.
I'm not gonna lie.
Hmm. So you took EGR, Ryan? 115?
Yeah, I did.
Hmm.
But I'm reteaching myself MATLAB right now. So
Hmm. Okay.
I know it now, but
Hmm.
like I don't ever actually remember
Hmm.
learning it in the
Okay.
class.
Yeah, okay. Do you actually use symbolic math for something like preparing for homework? Actually, anybody's comment welcomed.
I
Not
use
really. Oh,
Wolfram
you
Alpha.
okay? So what class are you using symbolic math typically?
No, I don't use symbolic math.
You
I
don't use
use
okay.
Wolfram Alpha.
Ah, okay. You don't use it. So you must be curious about okay, how can I pick up symbolic math and actually start using for some classes? Okay. So hopefully, so this is if you click here, this is the lecture note which I developed for EGR 115. By the way, am I going to teach EGR 115 this fall? I think so. So this is something I probably need to review and then be ready for fall semester. But this is taken from last year's EGR 115, actually summer. Yeah, last year summer I taught EGR. So this is the note I developed. So obviously I'm not gonna do a lecture of MATLAB now because it's kind of redundant. So MATLAB, one of the greatest feature is students don't realize, but you can run it by yourself. Everything. Okay. So funny thing is MATLAB, when I was an undergraduate student, I think MATLAB version 2 was something I picked up. That was very early days of MATLAB. Okay. Back then, computer language class I had to take was a Fortran. Okay. Fortran 70. Now, EGR 115, you actually take MATLAB class and then this is the first encounter for computer language, usually. And then, interesting thing is, I'm teaching MATLAB. Then I question myself, how did I learn MATLAB? Did I take MATLAB class? No, I I just picked up the software, started to use. That's how I run. It's funny. Even I'm teaching MATLAB right now. Never taking MATLAB class or anything. I just picked up all the knowledge all by myself. That's MATLAB, okay? So Ryan's making interesting comment. You're trying to kind of pick up lots of knowledge of MATLAB. That's actually very natural. And then I would encourage you, okay, pick up lots of knowledge here. So this is one of those interesting small tiny toolbox MATLAB is now associated with a standard package. So I'm just going over very quickly. So I'm talking about, so what is the MATLAB toolbox anyways? You hear MATLAB, this toolbox, that toolbox. You hear that all the time. That is actually correction. Okay. Okay, this is the package. It is a collection of MATLAB code, data, apps, examples, and documentation. Everything is included, and then make it as a package. This is called toolbox. So this is add-on, and then oftentimes this is kind of similar to like a extended. Extended is important, so this is not only that, but extended UDF. Do you know what is UDF? This is actually MATLAB extended UDF. User-defined functions. MATLAB is all about functions. And then users can also define functions for MATLAB, and you can add on, right? This is a package of extended UDF. So you can actually build your own MATLAB software and then register it as a toolbox. Okay. Tremendous amount of toolboxes are added every time for the new release comes up. And then those are just a few examples. And of course, you know, we have aerospace toolbox. Have you ever seen that? Aerospace MATLAB toolbox. It's very nifty. Okay, if you know how to use it, it's gonna save your life. This toolbox contains such as supersonic speed, shockwave versus Mach number conversion, like a flight path, flight control type of things, structural analysis, lots of things. Okay, standard atom sphere computation. This is one of those toolboxes somebody designed and built, and then now MATLAB accepted and registered as a standard package of the software. And then, of course, symbolic math is, this is one of the early ones. And then, of course, Simulink started as a toolbox to begin with. Now it's actually independent software by itself. Okay. So now, if you look at symbolic math, people just don't know how to use it because they don't know what it is. They don't know the purpose of using symbolic math, pros and cons. Okay, but MATLAB now supports the RIBE script. Do you guys know RIBE script, by the way? If you took your MATLAB class, did your instructor cover RIBE script?
Mine didn't.
Anybody else? So your professor typically covers only script, right? You guys know script, right?
Yeah.
Yeah, okay, so this is MATLAB script. What is MATLAB script, by the way? What is it? What is MATLAB script?
They're just a bunch of code that you
Yeah, it's a
just
dot
write
M.
down.
It's a dot M.
Oh yeah.
Yeah, that's right. Dot M file, isn't it? So this is basically a bunch of codes in it, or just a collection of MATLAB functions. Typically built-in functions you gather together, come up with your code or MATLAB script. It's usually called .m file. People call that always. They just run .m file to get things done. That's called MATLAB script. Now MATLAB nowadays has a RIBE script. This is not the .m, .mlx, RIBE script. Okay. So when you use symbolic math toolbox, okay, I would say you better use RIBE script. Okay, it is actually possible. Technically speaking, it's possible to use symbolic math toolbox with regular script, but I would say there's no meaning for it. It doesn't make any sense to me. So symbolic math toolbox always is associated with RIBE script, almost always. So that's the bottom line. So what is the RIBE script? Well, it's the script, but it's RIBE. Okay. Now, when you do scripting, okay, when you code your MATLAB code, what kind of tool do you use? You usually open up something and start typing your code, debug and run it, right? What is it? Let me show you. I'm running MATLAB right now. What's this? You open up a script. Then you actually start developing your code, right? What's this? you want to create the MATLAB script. You open up a new script, then you start typing. What are you using here? What's this? What's
Is
this?
that where your formulas go?
Yeah. Well, what's this, by the way? What kind of thing you're using right now?
Script file? I don't know. Editor?
Editor, yes. This is MATLAB editor. This is where you basically type something. Okay, you just start with percent mark, make a comment. This is MATLAB editor. Then do something, okay? Usually you start with like a CLC, clear, close, or something like that. Then making code. Well, this is like a typical pattern that you're going to create the MATLAB code, and then this is editor, and then you save it as a .m file, isn't it? Save as anything. Well, test demo, save. Yeah. Not the 2 words, sorry about that. Demo 1 or something like that. Anyways, yeah, so now you saved demo 1 to your file location. Okay, this is current file path. Demo 1 is saved up. So next time, okay, so you can close this one up, and then when you double click demo 1, you open up basically MATLAB editor here. This is what you usually do, scripting of MATLAB. Computer code development. So let's just go back to here. So now MATLAB actually offers RIBE script and then RIBE editor associated with. When you do symbolic math, make sure you use RIBE editor with RIBE script, okay? So this note, actually, if you take a close look at it, it actually gives you some introduction of RIBE editor, and then a few examples here. I'm not going to go over those examples, but the example exercise files are given already to you. So if you're interested, please do it by yourself, okay? So anyways, RIBE editor, I'm going to show you RIBE editor right now. So I'm going to close out this MATLAB editor. This is just a scripting editor. Close it. I'm not using. So I have a few already pre-coded RIBE editors. Let's just open one of them. Example 411. This is not the .m file, as you can see. This demo 1 is .m, but this is not. This is .mlx. So you can create, picking up a new RIBE script, not the script, RIBE script. And then it is going to open up a new .mlx file so that you can actually open up, not the editor, but this is RIBE editor. Can you see that? RIBE editor. What is the difference from editor to RIBE editor? Obviously, this RIBE editor has 3 different modes. This is the output on write mode. So this is your code. This is your output. So as you type something, you can see the output. That's called RIBE editor. Okay. And you can see this is like line by line mode. So this is your code. As you type in, you can actually execute. You just put run. Then it basically runs line by line by line by line. So as you type, you can run. You can get the result here. As you type, you can run. You can get results here. you type here, you can get results here. Or you can see those side by side. So this is your code, this is output. You can type and run at the same time. This is lib editor, okay? So MATLAB is being interpreter. That means every single line is interpreted as you type. That's the true interpretation of MATLAB. This is essentially what the MATLAB is originally designed for. So the scripting of MATLAB should be a lib editing. Okay, so this is where MATLAB is heading for. Now the problem is this is usually not so nice if you are just doing regular computer programming, because you don't have to run every time you type something, right? For the regular computing, you don't need to see the results of every line. But there is a type of work you really want results every line. What kind of work? Symbolic mathematical operation. That's why you need the lib editor. Okay, so understand the very basic concept is important. Why do you choose this? Why are you using it? What's the benefit? People just don't understand those things and then use the lib editor for just about anything. And then I basically say, why do you use lib editor? Oh, because it's new and cool. That's not the reason. Okay, just the regular programming, you don't need this kind of thing. Because I'm doing symbolic math, I need a lib editor. That's why. Okay. So, anyways, let's just go back to today's lecture. So this is just a brief introduction of MATLAB. Okay. So I'm going to minimize my MATLAB right now for a moment. Okay. So please, if you're interested, this is just a self-learning material, comes with lots of exercises. I'm not going to go over those exercises, but symbolic math toolboxes MATLAB can do just about any math you can think of. You can differentiate, you can integrate, you can find the limit, you can sum or simplify expression, evaluate, substitute the plug in the number, get the number out kind of thing. You can do just about any math you can imagine. And then interesting feature here. You can actually do engineering analysis associated with the engineering units. Let's say, you are analyzing something that actually comes with units, and then you can actually mix up SI units and then US standard units, in which it's a devastatingly terrible thing to do by hand, but the software can handle. In other words, two different kind of units you can mix up, and software can automatically convert. Okay, kilogram or kilogram analysis. Is this a kilogram mass or kilogram force? Software can handle that. Is this this is pound mass or pound force? Well, software can handle those things. Okay, units. This is actually quite important. So you can actually associate the number with units, and then as you compute, unit automatically carried across the computation so that the appropriate units comes out. Okay, so you can minimize the mistake associated with units. Okay, now good. So this is an example problem. What's this? Let's just take a look at the example problem here. Okay, consider a low-speed commercial aircraft Cessna in flight at a standard sea level equivalent atmospheric condition, but under the gravitational acceleration of 27 feet per second. Oh, okay. This is not the standard condition of gravity at sea level. Over the wing of this aircraft, the air pressure and temperature measured are those. Huh. Okay. Calculate the corresponding specific weight of air at that point, both in SI and US customary units. Now, people actually use MATLAB trying to solve this problem. This is example 7.1. Let me just take a look at example 7.1. Okay. It's not here. Sorry. This is EGR class, so you have to do it by yourself. But anyways, there are three different kinds of solution. One is a total nonsense type of solution. This is a regular script type of solution. It looks nice, but what's the point of doing this? That's my opinion. So this is a total nonsense solution. This is okay solution. In other words, you are going to actually use MATLAB Ribe script associated with the units. This is a symbolic mass. Best way is actually you have a software, something called S-Math Studio. If you use this software, this is super easy. But by the way, this S-Math Studio, what the heck is that? I'm going to show you later, but S-Math Studio. You can basically click here and visit by yourself. Okay, I'm not going to do it. All right, so please do it by yourself if you're interested. Okay. All right, so this is, by the way, example 7.2 of EGR 117. This is, here we go, class example 411 of ES201. That's what we are trying to solve it today. It's the same problem. Here we go, okay? So basically, I cut it, paste it from ES201 nodes into EGR 115 nodes, creating the same exact example problem here, okay? So let's just take a look. Go back to ES201 today. Example 411, page 6 of your note. Let's just take a look. Determine the distance x over bar to the center of mass of the homogeneous rod bent into the shape shown. If the rod has a mass per unit length of 0.5 kilogram per meter, determine the reactions at the fixed support O. So this is the center of mass. Here we go. If this is under the standard gravity of Earth, this is often called center of gravity too. Okay. So what is the process of finding such a thing? First of all, you want to know x over bar, the distance x over bar to the center of mass. Okay. So I think the process is essentially we covered yesterday. Center of mass. The origin all the way from back is the center of gravity. In other words, if you are given a series of particles, each come with the weight. Okay. So if you sum all of those weight, it is the resultant weight. And you are going to basically set the distance x bar, y bar, z bar to the location of g. This is called center of gravity. Okay. Now, how can we find out such a thing? In other words, this is the center of gravity of all of those particles. You can find out those things by sum of all the moment that can possibly be created by the presence of weight. Weight is a force creating the moment at each axis. This is called x over bar, y over bar, z over bar. So x over bar times w gives you the moment divided by the resultant weight. Is going to give you the location to the center of gravity. Okay. And then center of mass. Instead of talking about weight, you're going to talking about mass. Okay. Now, the center of mass is given by assuming that the acceleration due to gravity g for every particle is constant. That means center of gravity becomes center of mass. So now we are going to apply for the rigid body. That means body is created by so many particles. So each one of those particles has its own weight, has developed the moment from each axis. So you are going to now turn it into not the summation but the integral. Okay, so this is going to be an equation of x over bar, y over bar, z over bar. This is the center of gravity, and this is the center of mass. In terms of density, this is also what center of gravity in terms of specific weight. This is the center of mass in terms of density. This is centroid, which is the geometric center. Okay. So we are talking about the geometric center of this, assuming that the bar is made up by the same material, something called homogeneous. That is, the center of mass is equal to the centroid if it's homogeneous. Okay, so that's the whole point. So we are going to pick up this equation. Because something is given as a bar, okay, it's a Rhine centroid. So what you need to be doing, suppose something is given, the Rhine is given, you're going to choose a small segment along the Rhine called dl. And then you're going to multiply x tilde. X tilde is, in this case, this is the x tilde. So this is the distance measured from z-axis to the location of this small tiny segment, dl. This is x tilde. Okay. Divided by integral of dl. Integral over the line of L dl. This is going to give you the length itself. Okay. So we are going to pick up this equation and apply to this. So center of mass, this is homogeneous, okay? So it says so, I think. Homogeneous rod. In other words, this whole bar is made up by the same material, exact same material. In that case, center of mass is equal to centroid. Okay? So along this length L, you are going to, okay, pick up any location is fine, but pick up small tiny dl. Okay. And then consider this coordinate position. This is called x tilde and also y tilde. This is the coordinate location of this small tiny segment dl. Okay. And then in this case, this is location x anyways. So in this case, x is equal to x tilde. Okay. What we want to know is there must be somewhere something called centroid. Centroid C. X over bar, y over bar. So this is the coordinate of the centroid C. It could be around the line of the bar or it could be outside of the bar anyways, but I would say I don't know. So I suspect this is a line integral. So the centroid is probably, yeah, so in this case, centroid is here. May not necessarily be along the line, you know, it could be offset a little bit. Area centroid is usually inside of the area. Volume centroid is usually inside of the volume, but the line, we don't know. So anyways, let's assume maybe my wild guess is probably here, around here maybe. So this is the location of centroid. I want to know where it is. Okay. So first of all, geometrically speaking, I want to once again draw a sketch. Okay. So this is coordinate y, coordinate x. This is point O. Okay, so this is the rod. Now, interestingly, this rod can be described as a mathematical function y squared is equal to x cubed. Okay. So if you draw a center line, this kind of curve. So this curve can be represented by y squared is equal to x cubed. So this is the shape of the rod. And if you take a close look at the relationship, okay. So suppose if you choose a small tiny segment dl, okay. You can draw like a sketch of a relationship. In other words, if this is dl, this is dy, this is dx. And then you can come up with a relationship of this whole thing. The relationship is y squared is equal to x cubed. Okay, so dl is now, by looking at this relationship, dl is square root of dx squared plus dy squared. So dl is square root 1 plus dy dx square times dx, isn't it? Mathematically speaking. So since y squared is equal to x cubed, you can basically say that y squared is equal to x cubed. So y is equal to x to the power of 3 over 2. So you can do dy dx, dy dx. You just differentiate dy dx is 3 over 2 x to the 1/2. Okay. All right. Okay, so far. So now we are going to apply the equation to find out the centroid or center of mass. The equation, what we want is x over bar. X over bar is, suppose if this is the centroid, okay, I assume it's probably around here, centroid. So what is the distance to the centroid, x over bar? That's what I want to know. And suppose if you choose here as a local small tiny segment dl, this is x tilde. Okay. So x over bar, if you look at the equation, you can find out by integral over the length L, x tilde dl divided by integral over the length L dl. Okay, so this is the equation to find out centroid or center of mass, either way. So it's coming from here for the line segment. Okay. So this is the center of mass or centroid in this case, the same thing because it's a homogeneous material. Okay. So now the question is, okay, well, good. So this is integral over the length L x tilde dl is this is x tilde is x. So just plug in x times this is dl, x times what, square root 1 plus dy dx is what? dy dx is okay. 3 over 2x to the 1/2 square. Close bracket dx. Looks like, because dy dx is that square. Okay. And then here is what? Integral over L. It's just that. Square root 1 plus 3 over 2 to the x to the power of 1/2 square dx. Then at this point, I'm going to probably start losing my motivation to continue on mathematical detail. But anyway, let's just continue. So this is integral. Then what's the integral range? Well, we want to integrate over x equal to 0 to 1 meter, because that's the entire length of the this rod. So okay, so if you integrate over the direction x, this is x equal to 0 to 1 meter, looks like. And this is what? X times x times what the? Okay, x times, I'm going to look at my cheat sheet. So this should be square root of 1 plus 9 over 4x. Really? Square root, really? Dx, is it correct? Could somebody please check it out? Is this correct? If you take a 3 over 2x to the half power, take a square. Is that right? Is that right? I think so. And the bottom, once again, integral from 0 to 1 meter. Square root 1 plus 9 over 4x dx. Then I don't want to do this anymore. Okay, so now I'm going to basically pick up the software. Do you understand what I'm talking about? Okay, so okay. So who actually wants to do it by hand? You can do it by hand if you want to. I mean, typically in statics class, the professors will probably move on with this mathematical, okay, so let's just integrate. So x comes into square root. Stuff like that, I don't want to do that. So this is the math, essentially. So my motivation is MATLAB symbolic math. Okay. Then you should get the answer. Something like 0.5457 meter. Do you have any question? Please react. Are you happy?
On the exam, we're not gonna be able to use MATLAB though, right?
I'm not sure. And then, yeah, well, let's talk about that later. But are you happy about what I just did? You feel like, wait a second, Professor, you didn't tell me anything. Okay. Right. So, okay, let's just take a look. So I'm going to switch back to EGR 115. Here we go, MATLAB class. So this is exact same problem. Okay, determine the distance x over bar to the center of mass of the homogeneous rod bent into the shape. So this is basically exactly what I just did. Can you see that? So this is the classic paper and pen engineering solution I just demonstrated here in ES201 class. Too bad you are a student of ES201, aren't you? So you have to go through hand math, something like this, or, you know, by the way, interestingly, can you do this? And then, can you do this? How would you do that? Do you know how to do this? You're that good for math? I'm not. I don't think I can do this. I pretend like I did it by hand, right? You know, but I didn't do it by hand. I used the software. Okay. So here's the answer, of course. But let's just take a look at the alternative solution using software. So this is MATLAB Live script. Of course, everybody should have a MATLAB. Do you have MATLAB, by the way, right now in your computer? How many people actually have a MATLAB installed in your computer and then have a Live script and stuff? Okay, good. So I hope you use it, okay? Otherwise, you have to do this hand math. Too bad. Even professor wouldn't be willing to do that. Okay, so I'm going to switch to MATLAB, okay?
Does MATLAB show you the steps of how it got to an answer, or is there just like
If you
something up in front of me right now?
if you want to show every step, you can see it. That's the beauty of a Live script, okay? Live script, like I said, it's a Live. In other words, you can see every step. As you type, you can see it, okay? Now, what is it? Example 411. So let's just open, oh, this is Live script. Here we go, Live editor, okay? So as a Live editor, you can manipulate. If you want to differentiate, you know, you see that? So I'm actually starting with y equal to x to the 3 over 2. This is the function given. Let me just bring it up. Okay. So what I want to see is seeing side by side. So what I'm doing is I'm doing like a hand calculation. Hey, this is a functional relationship between y and x, y and x. What I want to know is, first of all, I want to differentiate and find out dy dx. I can actually do that using here, symbolic math toolbox. So I'm going to set this is a symbolic variable. Symbolic variable is x is just x. It's just a variable. I'm just going to use x as a variable. It's a symbolic, okay? So this is symbolic variable, x is defined. Now I'm going to define y, another symbolic variable, as a function of x. So this is y as a function of x. Here we go. I constructed y as a function of x. So what I want is, hey, I want to differentiate this. dy dx. What is dy dx? Hey, this is dy dx. Yeah, oh, okay. So now I'm going to go back to my note, right? And Oh, dy dx is this. Looks like, did I do this by hand? Not really. I just used the MATLAB. Anyways, so now this is dy dx. Here we go. I found it. And next thing
Professor,
is, go ahead.
why did you even differentiate dy dx? Like,
Well,
where?
because I need it.
Yeah, but like, why do you need it?
Because dy dx is part of this integral function.
Oh, okay.
Let
Okay.
me just show you my other notes. This is what I just did. Okay, this is much better probably to look at it. So this is the original functional relationship, y and x. That means y squared is equal to x to the cube. That means y equal to x to the 3 over 2 power. Okay. And then I want to plug in this dy dx into the function of dl right here. So I really needed to plug in. Yeah, so that's why. So this thing needed to be plugged in here. Then after you're doing that, you come up with this or
Okay.
that. Yeah. Then after that, you have to even integrate. So so there are lots of mathematical manipulation I have to do, and then I was lazy. I didn't want to do it by hand. So I actually used MATLAB. So after I differentiate, I come up with dy dx comes again. So this is a function of 1. Obviously, function of 1 is constructed by dy dx plugged into the original function, square root of 1 plus dy dx squared. Let me just show it side by side. I'm going to probably show it like this. Okay. Okay. So I set the y as a function of x right here. Actually, this. I started from here, and then dy dx, I just found dy dx, and then I constructed this function by plugging in. Now I know this is square root of 1 plus 9x over 4 right here. That's coming up here. Function 2 is like x multiplied by that. It's going to be constructed here. This is the coming in here. So this is F2 right here. This is F2. This is F1. Each one of those F2 and F1 I can integrate over the range. So this is integral. Integral to find out x bar. So this is integral of function of 2 in the range of 0 to 1. This is what? That's what this thing is. So this is the integral from 0 to 1, integral of function of 2, 0 to 1, divided by integral of function of 1, the range is 0 to 1. If you take the ratio, that's the x bar. Then MATLAB actually does the calculation. This is actually completely symbolic results. Oh my goodness, I don't need that. Just simplify it. Okay, I can simplify as much as to this point. Okay, just to make it the real number. This is a double precision floating point variable expression, not the symbolic expression anymore. So now it's 0.5457. Oh, okay, good, cool. That's the answer. That's what I did. Okay, so I didn't use my brain. I used my software because I'm not mathematician. I don't need to know the detail of those. I need to know how to use the software to get to those results. And then software cannot make mistakes. So that's what I'm thinking as an engineer. I'm not a mathematician. I use software. So this is one such technique to use software to do this kind of math. I guess the alternative choice is, well, you just do hand math. I guess the traditionally speaking, any other, statics class, sorry, mechanics class, if the problem is involved in, okay, let's find out centroid or center mass, you have to probably do this math. I completely avoid it. Do you have any question? So do you think you can use this for the rest of this homework assignment? Or
Yeah.
would you like to do it by hand? Either way, I mean, it's your choice. Okay. So typically, the statics class requires to do this hand math by yourself. In other words, you have to go back to your old mathematics textbook or something like that. You have to remember, do all the hand math. If you do such a thing, I guess the typical result is where this is your typical result. But you notice that I'm skipping lots of details from here to here. Skipping lots of details. I'm skipping also lots of details from here to here. And quite frankly, I don't know those details because I use the software. And I'm not even interested. I'm not a mathematician.
Do we need to know those details ourselves? I mean,
I don't,
in our work and all that?
I don't care. It's not my job.
Okay.
I assume you know because you took math classes.
Right.
I'm so I guess bottom line is okay. If this is an exam, I don't think I would give you this kind of math. I try to choose the problem that actually making the math super easy so that I can even do it by hand kind of problem. I probably limit myself for the exam. But I guess in reality, you know, after you complete this class and move on to solid mechanics, I guess you have two choices. Number one, okay, you do this kind of math all by hand, just like traditional statics professor says. I'm not a traditional static professor, and I'm not a mathematician. So I use software, but if you choose to go with that route, you have to master how to use the software. So you have a choice right here, right now. You can choose, okay? So this is, by the way, yeah, it's just a cut and paste of my code here, the same code. This is the solution done by Symbolic Math Toolbox in MATLAB. Here we go. And we do have even better solution. Do you know what it is? This is probably the best solution. You would love to have this kind of solution. Do you know what this is? This is probably the best. This is the Symbolic Math software. Okay, so let me just show you this solution. This is it. So this is something called MathCAD, PTC MathCAD. This is the actually not the free software. I do have a subscription of PTC MathCAD as a research license. This actually costs $500 a year if you want to subscribe. So you can't use it. But this is the symbolic software. You know the expression here. If you want to integrate in the range of x from 0 to 1 over this kind of function, you just type in the function and boom, that's it. You don't have to even do any math. So this is what I usually do. This is the symbolic math software called MathCAD, PTC. This is a professional version. You can't use it. So this is the freebie version, S-Math Studio. Okay. If you're curious about this, well, just go ahead, dig in. I started to use PTC MathCAD when I was a graduate student a long time ago. And back then, I donated all of my calculator to someone else because I never used the calculator since then. All the math computations are done using MathCAD. Okay. Quite frankly, I don't need any calculator anymore. So whatever the solution I offered for you this semester throughout, even though it looks like it's handwritten, but everything is done by software. So there's absolutely no mistake guaranteed. Unless I type in the wrong value. Okay. Analysis-wise, I cannot make mistakes because analysis is done by software. It's not by hand. So if you're interested, of course, you can start doing it. It's going to take years and years to develop this kind of skill, but I started when I was an undergrad student. Okay, so it's all about motivation. So anyways, so this is probably the best solution. This is classic solution. This is what you can do now because you have MATLAB. It's a free software. So it's your decision. Okay. So let's just go. Do you have any question? Any questions? Fine. Just don't hesitate. If you want to really grab a real skill set, you have to really aggressively ask lots of questions. Staying quiet, you're not going to get anything. Any question? Anybody? Don't hesitate. I'll be happy to share anything I have. This is end of the summer, 3 more days. Okay, don't waste your time. If you're curious about certain things, I can share. This could be your only chance to take my class. Probably not, because you have to take Aero. Any question? All right, so let's just go back here. So as you showed you, I got this result using software. That's me. So like I said, 3 different choices. Number 1, you just do a hand mass. Of course, you can possibly do it. I don't, but you can. Number 2, you can use MATLAB Symbolic Math Toolbox, which I provided you every material you need. If you want to self-study, go for it. Okay. Number 3, of course, to do symbolic math software just like this, I'm using PTC MathCAD professional version. You can actually download SMath Studio, which is a free version. 3 choices. You just make your own decision. All right. So let's move on. This is homework, okay? Homework 411. Determine the location both x over bar and y over bar of the centroid of the wire, which is very, very similar to what we just did here. By the way, one of them is already known. Which one? X over bar or y over bar? You know one of them already. Which one?
Y bar. Because it's in the center, right?
You're talking about x bar. X bar is 0.
Oh, it's X in this. Yeah.
Yeah, that's right. That's right. Okay. Yeah, I appreciate your wrong response. That's fine. So you know already x bar is 0. Then the only thing you need to know is y over bar. Okay. So in other words, centroid is along this y-axis because it's a line of symmetry. This is axis of symmetry. That's y bar. So x over bar is 0 always. So my guess is probably around here. This is the centroid. This is x over bar, y bar. And this is 0. You already know. Okay. So the rest is very similar process. Okay. And then again, the functional relationship is given for this shape. Okay. So you have to find out using this equation. Okay. And do you do it by hand or do you use your software? I don't know. It's your decision. I don't care. Like I said, I did it using software. Okay. Next page. Oh. Locate the centroid x over bar of the shaded area. Now, this is quite interestingly, you have to manipulate as a pure mathematical function. So the result is going to be some kind of mathematical expression. Do you think the software can do? Indeed. So let's just take a look. This is an example. I have to do it. Okay. So this is, okay, centroid x over bar of the shaded area. So this is area integral, isn't it? Oh my, area integral. So it is a double integral or integration of the line multiplied by some fixed value. Either way, this is area integral. So let's just go back to find out the equation of area centroid. Is this x bar? Yeah, that's right. So x over bar of the shaded area. So this is the equation for it. It is a similar. So this is a line integral. So this could be a single function of x, but this is area dA literally means this is, if this is xy, this is integral over the x, integral over the y, dy dx, if it's xy plane. So this is inherently double integral. You have to be very careful about that. That's what the area integral really is. Okay, so let's just apply this equation. Okay, so we are going to find out, first of all, okay, so since this is area integral, you have two different ways to find out. Actually, this is centroid x over bar. Suppose I can easily create a variant of this problem. Okay, let's find out the centroid also y over bar. Well, because this is a centroid of the area, that means you need both coordinate x over bar and y over bar. So this is only half of it. Okay, so my guess is, bullseye of the geometric center of this geometry is, I don't know, somewhere around here, called centroid. Okay, so this centroid has a coordinate. This is x over bar. This is y over bar. In other words, this is a coordinate x over bar and y over bar. So this is a centroid. So this is only half of the question. In other words, hey, let's find out x over bar. Well, I can easily create another problem. Okay, so how about finding y over bar? This could be easily a quiz problem, Okay, anyways. So let's just do a sketch here. So this is a coordinate y, coordinate x, and this is the shaded area. It's probably expressed by mathematical function. So this line can be represented y as a function of x. This is 2 times k x minus x squared over 2a. So this is a mathematical function. This is a straight line. And then you have a geometry of that. It's k times a. K is some kind of constant, I believe. So what you are going to do here, you're going to basically choose a arbitrary location. Okay? Arbitrary location x. Then you are going to choose small, tiny strip cut. So this is the dx. Okay? Now let's just zoom in what you just cut out. So this thing is, if you really zoom in, you're going to actually check out this kind of thing. Since this dx is so small, so this is dx is so thin, you are going to assume that this is just a rectangle, even though this is certainly not rectangle, but let's assume this is rectangle because dx is so small. So this is the height y at that point. And then you are going to identify the centroid of this small tiny segment. This is a local centroid, okay? So this local centroid has a coordinate x tilde and y tilde. That's what it is, okay? And this is the area dA. Okay, obviously area dA can be given by y times dx, isn't it? Y dx. So, okay, so I have to do a little bit of math, but okay. Before doing that, let me just identify. So this is the local centroid, which is x tilde y tilde. Okay, and obviously x tilde is equal to x by itself. Y tilde is obviously half of y, isn't it? So y tilde is half of y. Okay, so that's y tilde. X tilde is x itself. Because of the shape, y tilde is half of y. So this is the local centroid of this small tiny cut segment, dA. Okay? So important mass. Okay, since dA is equal to y dx, I just plug in the function. Function y is given here. So y is equal to 2k x minus x squared over 2a dx. So this is important. Okay, so now I'm going to move on and then pick up the equation for the centroid x over bar. This is the area centroid, so this is integral over the area x tilde dA divided by integral over the area dA. Okay, so this is, now we defined that this dA is this. Now dA, I just turned into the single function of x. So this is actually area integral, but since y is a constant, actually a function of x you can specify. So this is actually area integral now turned into the line integral in the direction of x. That's what I'm doing. So this is going to be actually integral from in the direction of x from 0 to a. So integral from 0 to a in the direction of x. X tilde is x itself. Now dA, we found this, x times 2 times k x minus x squared over 2a dx, close bracket here. Okay, so this one is also integral from 0 to a in the direction of x. So 2 times k times x minus x squared over 2a dx. Okay. And then what? Now you turn into mass. So I used MATLAB. Okay. So MATLAB symbolic mass toolbox. Let me just take a look at it. Okay. Example 412. Let me just open up. Here we go. So this is, like I said, drive editor. So class example 412. So let me just put it side by side. Okay. So what I want to do is this mass. So using MATLAB here. So first of all, I just define this is a symbolic variable x, symbolic variable k, symbolic variable a. 3 symbolic variables I defined, and then I constructed this thing, dA. Okay. So it looks like dA is y times dx, which is 2 times k times x minus x squared over 2a. Oh, dx is missing. Oh, yeah, it's okay. dA, okay. So that's dA. X2 is x, yeah, sure. So I constructed the function 1 and function 2. Function 1 is dA, which is this. This is function 1. Function 2 is x times that. So this is function 2. So x bar is integral of function 2 in the range of 0 to a divided by integral of a function 1 from the range of 0 to a. You get this result. Here we go. Result is 5a over 8. Okay? If you do this by hand, in which I didn't do it by hand, but if I pretend like, hey, you can do this by hand kind of thing, this is the solution from here to here. Can you do this? I'm not sure. So you multiply x, so this becomes x squared, this is x cubed. Yeah, that's right. You can possibly do this. So this is the 2kx squared. So if you integrate from 0 to a, you're going to have a 2k goes outside. So this is x squared. So x cubed over 3, this is x cubed over 2a. So this is x fourth over 8a. Yeah, you can do it by hand. That's right. Evaluates from 0 to a. In other words, 2k a cubed over 3 minus a fourth power divided by 8a. A goes cancel. Okay. So this problem, you can, by the way, from here to here is fairly simple. You can actually do it by hand, right? As you can see. Obviously, I didn't do it by hand, apparently. So I used the symbolic mass to find out the same result. Okay? So it's your choice. You can either try to attempt to do everything by hand math, or you can pick up this software, challenge yourself, self-run, how to use the symbolic mass, and then do all the math using software. This is the symbolic. In other words, this is a mathematical manipulation. MATLAB can do it for you. Okay. All right. Any question? Next page. Next page is homework. Okay, very similar. Locate the centroid x over bar of the shaded area. Wow. X to the power of n comes in. I'm not sure if you can do hand math or not. Like I said, I never do hand math anyways. I always use the software. So, again, I would highly recommend you, explore the symbolic math of MATLAB. Okay. All right. So let's just move on next page here. Next is a composite bodies. A composite body can be divided into several simple geometries. So what is the typical example of composite body? Let's say this is a cross section of a beam. I-beam. Where's the centroid? Okay, well, this is a composite body. Why? Because you can divide this beam into 3 segments, just like this. This is a segment 1, segment 2, segment 3. And each segment has its own centroid, yeah? This is centroid of segment 1. This is the centroid of segment 2. This is centroid of segment 3. Okay? Then you can determine, the centroid of this composite body, the entire cross sections, where is it? You can determine by summation of all of those things. Okay, so you can calculate the center of gravity and centroid of composite bodies First of all, creating specific simple geometries, and then you're going to create the table. Okay, so this is called table method. Okay, I think probably this is only me using this. This is a table method I basically developed. Okay, so I made up table method when I was a student. I realized, hey, this is easier than any other method to determine composite body centroid or center of gravity. The point is being, suppose you are dealing with lots of complex geometries. This is simple geometry, only comes up with 3 parts. Suppose if you have a gigantic system with like thousands of different parts, you probably want to develop a computer code which is based on this table method. You can easily apply to that application. So that's why table method. So I'm going to share you the method I invented by myself when I was a student. So let's just take a look at the table method application to find out centroid. Next page, okay? So let's just take a look at the class example 421 table method based. Let's find out the centroid y over bar of the cross-sectional area of this channel. Okay, so this is the centroid. You want to find out this. Okay, so obviously you're going to create 3 different simple geometry out of this. Okay. So this cross section is made up by three different parts. Okay, so that's just a property label. This is part 1. This is part 2. This is part 3. So 3 different parts, okay? And then second step is you are going to identify the local centroid for each part. Right here, and right here. And then properly label that. Measured from some reference point. Okay, so we are going to determine the reference point. I'm going to actually inverted triangle. Do you know what this sign is? This is datum. Datum or reference line. Reference point. You are going to measure everything from here. So, part 1. What is this distance here? Anybody? This is the local centroid of this part. What's this distance?
Would it be 3 inches?
3 inches, correct. That's right. How about this? How about this?
1 inch.
1 inch, correct. This is the same as part 1. So this is 3 inch also. Okay. And then important thing, I want to clearly define 2 different things. Okay. One is y over bar, in which this one, okay? Y over bar is something we want to find. This is the centroid. Of the entire cross section. This is a composite body. Composite body measured from reference line. Of course, reference is here, so everything is measured from here. Obviously, it looks like. Okay. And then the other thing is quite important. You have to clearly differentiate y tilde. Those are local centroid. Of each part, okay? So this 3-inch is y tilde of part 1. This is y tilde of part 2. This is y tilde of part 3. So you have local centroid for each part, obviously. So let's just be very, very, very careful. So I'm going to draw a table. I'm going to use the table every time I see the composite body. This is a standard for my class. I don't know about any other professor, but I do this all the time. So I'm going to create the table. Go ahead, question.
Professor?
Go ahead.
Yeah, is it exactly in the middle because it's homogeneous material?
This is a homogeneous material. Yeah, that's right. So again, centroid doesn't actually care about the material. Centroid is a geometric property. So material doesn't matter. So if you start talking about material, you're talking about center of gravity or center of mass. If it's non-homogeneous, yeah, center of mass or gravity depends on type of material.
Okay, thank you.
Yeah, so this is homogeneous. So we basically say center of mass, gravity, or centroid all the same. Okay. Anyways, good question though. So I'm going to let's just take a look at part 1 and 2 and 3. And then this is sigma, which is summation of all of those parts. And then here I'm going to basically say A is area. In this case, inch square. So part 1 area is, this is a 2-inch, right? Okay. So part 1 is, area is a 2-inch. Multiplied by that is 6-inch. 2 times 6. This is 12-inch square. Part 2 is like what? 12, okay. 12-inch multiplied by 2-inch. 24-inch square. Part 3, exactly the same as 1, 2 times 6. This is 12-inch square. Next, I'm going to list y tilde of each part. This is inch. Obviously, this is a 3-inch. Part 2 is 1 inch. Part 3 is 3-inch. Okay. Now I'm going to do y tilde multiplied by area A. Okay, so this times that, 36. By the way, this is the unit of inch cube. So 24 times 1 is 24. This is again 36. Then I'm going to add them up all the area. 12 plus 24 plus 12. This is 48. This is the summation of this. This is also sum all of those 3. This is going to be 36 plus 24 plus 36. This is 96. Okay, good. So from here, what you can say is centroid of the entire cross section is summation of, oops, 5 more minutes. summation of y tilde a divided by summation of a. This is going to be 96/48, 2 inch. I didn't even need a calculator. So this is so convenient. So this is 2 inch. So this is how I determine the centroid location, at least in this case, y distance of this composite cross section. Obviously, the centroid location of x over bar is 0, of course. This is the axis of symmetry, right? So x over bar is 0. Y over bar is 2 inch measured from the top of this composite structure here. Okay. So you are going to do the same method. You're going to construct the table to do this. Locate the centroid y over bar of the cross-sectional area. Obviously, you're going to come up with this part, that part, and this part. Looks like 3 parts. Part 1, part 2, part 3. This is the y-axis is the axis of symmetry, so x over bar is 0 in this case. So only thing you need to know is y over bar measured from here, I think. So what is the y over bar measured from here? Okay, so this is a reference. Okay. Next page. Again, the very similar problem. Okay. I think this is the reference line. You are going to measure everything from here. What is the centroid y over bar? Obviously, you have this part. And I don't know what I did. It could, yeah, this part to this part, that part, or this part and this part. I don't know. Oh, yeah. But I think the result is the same. No matter what kind of part section you choose, your result should be the same thing. So it could be like a choice of like this and this and 2 part, or this 3 part, or it could possibly 1, 2, 3, 4, 5 different parts. You can choose any sections, but the result should be the same. I guess the table gets bigger. That's what it is. Do you have any question here? So this is the end of Unit 4A. Do you have any question? So hopefully you spent some time trying to kind of get started on MATLAB symbolic math. It is going to be powerful tool, and you can use this symbolic math for any other class of engineering. Okay, so I think it's worth attempting to solve some homework assignments using MATLAB symbolic math toolbox. So I would strongly encourage you to do that. So have a good day. Let's stop here today. Okay. And then see you guys back tomorrow. We have 2 more in-class lectures to finish up this summer. Have a good day.
Thank you.
Thank you.
Thank you.
Thank you.
Yep. See you tomorrow.